last presentation of the session is size change terminations contract, and Phil Wen is the speaker.
Hi, I'm Phil, presenting our work on size change termination as a contract, which is about language support for detecting non-termination at runtime. This is joint work with David Van Horn, Sam Tobin-Hochstadt, and Thomas Gilray. To have an idea of what termination contract does, let's look at some examples. Suppose we write ackermann. In the ideal case, we get it right the first time, and the function terminates on all inputs with the right answers. In a not so unlikely case, we make a mistake, and the program keeps running, and we have to kill it after a while. This is less than ideal, because long-running computations are usually ambiguous whether they're infinite loops or just low progress. With the use of a termination contract, we're guaranteed that as soon as ackermann enters an infinite loop, we get an error message. And as long as we see the program running, we know that it's making some kind of progress. If this example is not interesting enough to justify the checking of termination at runtime, let's look at a slightly more sophisticated program, the scheme interpreter running ackermann. Interpreters of Turing-complete languages don't always terminate. So let's say in this case, instead of asserting that the interpreter itself terminates, we'll just assert that the interpretation of ackermann terminates. Then things proceed as expected, where the interpretation of the correct ackermann program terminates with the right answer, and the interpretation of the buggy ackermann program that would produce an infinite loop gives an error message. So we've seen one motivation of why it can be useful to formulate termination checking as a runtime contract. Compared to static checks, termination contract can accept more terminating programs thanks to the extra precision that comes from the ability to observe concrete data and control flow at runtime. Another motivation is that runtime checks can integrate well with the existing higher order contract system, both benefiting from and adding value to the existing contract system. For example, the contract monitor in Semantics has blame, which allows pinpointing the exact party that doesn't hold up to the contract. If a party asserts termination and is blamed for non-terminating, then it can either fix its code or attach termination contract to the code that it has no control over. Termination contract can also compose with function contracts and allow function contracts to enforce total correctness as opposed to just partial correctness. And with this ability, an existing static contract verifier can also be used as a theorem prover in the language where total and partial functions can mix. And with function contracts that can enforce total correctness, this work potentially opens the door to sound gradual integration between dynamic and static languages where even when the static language is able to express total functions. Another motivation is that with an operational semantics for checking termination at runtime, we can straightforwardly derive a static verifier for termination the same way as we would for any safety property. So for the rest of the talk, I'm going to go over briefly the background of size change termination. Then I'm going to show an operational semantics for selectively enforcing termination in the program. Then I'm going to show the evaluation of the effectiveness and runtime overhead of termination contract. So size change termination is a simple and general principle for checking termination of programs that have some kind of well-founded partial order in their data. The principle states that the sufficient condition for a program to terminate on all inputs is that every infinite call sequence in the program would cause an infinite descent in some data values. In the original work on size change termination, the way that the static analysis works is that given the control flow graph of the program, it annotates each function call in the program with what's called a size change graph, which is a bipartite graph between the arguments of the caller and the arguments of the callee, recording how the former descends to the latter For example, one way that ackermann can call itself is as in this highlighted expression where the caller's first argument strictly descends to the first argument of the callee. And the same can be said for the outer recursive call. For the inner recursive call of this buggy ackermann program, the only relations that we can prove is that each argument maintains from the caller to the callee. So the compositions of size change graph are size change graphs that describe how arguments descend across transitive function calls. So if the analysis is able to detect a cycle in the control flow graph such that it has a size change graph that violates the size change principle, in the sense that if the size change graph lacks an edge that strictly descends from one argument to itself, and that if that size change graph is idempotent, which means that composing that size change graph with itself use the same size change graph. If that is the case, then the analysis has detected a potential infinite loop in the program. If instead the analysis is able to prove that there's no cycle in the program with that size change graph, then it's successfully proven that the program terminates on all inputs. So size change termination has proven effective in checking for termination of many functional programs beyond simple structural recursion without any annotation from users, such as lexicographical order or permuted argument, and so on. So there are multiple sources of approximations that make this notion of termination conservative with respect to the true termination property. First, size change termination is a particular way to terminate. The analysis is parameterized by a well-founded partial order, and no matter how sophisticated the order is, we can always have a program that descends not following that order. And finally, the analysis first relies on a control flow graph, which can be a significant approximation of what actually happens at runtime, especially for higher order programs where multiple functions at runtime can be conflated at static analysis time and create fake loops. So in our work, we separate the size change principle from the analysis the way that it was originally presented, and we transplant that principle into the context of runtime monitoring, where we guard the execution against any violation of the size change principle by observing the size change graphs that follow from the actual function calls as runtime. So any monitored program terminate either by adhering to the size change principle or by violating it and gets conservatively aborted. So before showing the operational semantics that incorporates this kind of monitoring, I want to show the visualized execution of applying monitored ackermann to 2 and 0. Applying ackermann to 2 and 0 result in the call to ackermann 1, 1, and the corresponding size change graph is as shown and is safe. Ackermann 1, 1 in turn results in the call to ackermann 1, 0. The new size change graph is safe, and its composition with the previous size change graph as explicitly shown here is also safe. The next call proceeds, and it's also safe. The new size change graph and its compositions with the previous two size change graphs that lead to ackermann 1, 0 is also safe. Because this program is safe, its execution is analogous to that from the standard semantics with the addition of constructing and monitoring the size change graphs. Suppose there was a bug in the ackermann program where the outer recursive call forgets to decrement m, then at some point, execution will reach a point where ackermann of 1, 1 calls ackermann of 1, 2, then the execution is aborted right there. So to formalize this kind of monitoring, we augment an existing standard semantics. Consider a big step standard semantics where an expression evaluates to a value under an environment. We augment it with what called a size change table, which tracks for each function the sequence of size change graphs that correspond to its recursive calls that result in the current evaluation, along with the most recent list of arguments that it was applied to that results in the current evaluation. Then the derivation of ackermann 2, 0 looks something like this, where we can derive the result for the the application only if we can derive the result for executing the body with an updated sidechain table, which has been guarded to be safe with respect to the sidechain property. In general, the non-standard semantics only differs from the standard semantics at applications, where before proceeding to executing the function body, we update the sidechain table and monitor it against the sidechain principal. Then during the dynamic extent of the function body, we use that new table. And if we detect a violation to the sidechain principal, then error is the only thing that we can derive. So that was the semantics for globally monitoring termination. Suppose we want to selectively monitor termination only for function with termination contracts, then we simply run the standard semantics and only switch to the non-standard semantics when we apply a guarded function. So the basic results are that this kind of monitoring is sound in the sense that it detects all non-termination. It obviously cannot be complete, but the kind of guarantee that it makes is that if the program follows this sidechain principle, then it's allowed to finish normally. So to evaluate this work, we implement termination contract as a library in Racket through two main modifications. We redefine what it means to apply, and we maintain the sidechain table using what called continuation marks. So an application in Racket can be thought of as syntactic sugar for this uglier form #% app, and any library that redefines this form as a macro can customize what it means to apply in any module that imports it. For our particular application, we redefine application to be this runtime case analysis that inspects the function that it's applying. If it's a guarded function, then we switch to the non-standard termination semantics. If we already are monitoring, that means we already are in the dynamic extent of applying some guarded function, then we continue with that non-standard semantics. Otherwise, we stick to the plain application in the host language. Then we maintain the sidechain table using what called continuation marks, which is a mechanism for annotating the continuation frames in the language with a value for each key in the way that when we return from one continuation frame, it restores to the previous value that's associated with that key, and the mechanism preserves tail call. So unsurprisingly, the naive implementation of sidechain monitoring is expensive, and there are a few optimizations that we can do to improve it significantly. First, we keep a whitelist of functions that are known to terminate on all inputs, such as many primitives, and we avoid instrumenting the application of them at compile time, at macro expansion time. Second, it's obviously very expensive to monitor the sidechain property at each function call. So what we do is we extend and monitor those graphs exponentially less often. In theory, this risks delaying the detection of non-termination, but in practice, non-termination often triggers a violation to the sidechain principle in early iterations, and for all our tests, we detect non-termination in no time. A final optimization that we can do is that instead of maintaining the sidechain table using continuation marks, we just maintain that using global state and generate code that brackets each application with code for updating and restoring the table. So this breaks tail call, but at least in the context of Racket, a loop of 10 million iterations, the imperative implementation is still faster than the continuation mark implementation. So we also derive a static verifier from the semantics, and there's not a lot of interesting thing about it, except that it's systematically derived from the semantics, just the same way as anyone would derive a static verifier to check any runtime safety property. So to evaluate this work, we collect a bunch of benchmarks from the original sidechain termination as a sanity check, and we also evaluate how it works on other work such as Liquid Haskell, Isabelle, and ACL2. So obviously, this is not a fair apple-to-apple comparison, but it at least shows that the mechanism is robust. In contrast, say ACL2 only handles first-order programs, and the type systems in Liquid Haskell and Isabelle cannot express some programs in the original higher-order sidechain termination paper. We also evaluate the static analysis that's straightforwardly derived from the semantics, and is competitive with the other static analysis. So we also look at the runtime overhead of monitoring termination for several programs. The factorial program, it does lots of work in each iteration, multiplying large integers. The sum program is a tight loop that does little work in each iteration. The merge sort program is more of a realistic loop that's somewhere in between. And we also evaluate their scheme interpreted variants. The overall result is that when there's heavy work in each iteration, there's little difference between the three implementations. And for the tight loop, that's where the overhead is the most pronounced, where the continuation mark implementation is significantly slower than the imperative implementation, which still has significant overhead over the baseline of an unmonitored program. Then the overall result of for the interpreted variants, where there's lots of work in each iteration, is that there's no significant overhead, is that the imperative implementation has no significant overhead. So in summary, termination contracts can accept more terminating programs, and it can be monitored with controllable overhead. Dynamic semantics are a good starting point for static analysis designs, and with function contracts that can enforce total correctness, this opens the door to sound integration of static and dynamic languages, where the static language can express total functions. And if you happen to use Racket, you can try it out. That's all.
Questions? Okay. Well, I'll ask when to get started. So you've got your static analysis derived from the dynamic analysis straightforwardly, right? What would you do? What next steps would you do to make that static analysis more precise, and what is missing from the straightforward translation of the dynamic into the static analysis?
Yeah. So the static analysis is derived from a method for straightforwardly obtaining an abstract interpreter from the concrete interpreter.
Yep.
And there's lots of knobs in there's lots of choice for trading off between precision and complexity, and we just picked a simple choice, which is monovariant, but we could do some more complicated analysis. Say we add more context sensitive to the analysis.
Okay.
Well, yeah.
All right, great, thanks.
Thank you. James McKenna, LFCS Edinburgh. What's the relationship between this work and online termination checking in Rybelchenko-Cook style terminator arguments, or more generally, well quasi-orders?
Oh, so as far as I know, so that work is more about checking for sophisticated termination for imperative programs, and we just focus on functional programs. So I'm not so sure about the soundness and completeness property of that work.
Right on time. Wow, that brings us to the end of the session. All right, thank you.